Okay, so the lab we're going to be doing tomorrow, okay, is on chemical reactions. So it'll be involving chemical changes, okay, chemical properties, what happens in a chemical reaction, all of that kind of stuff. Right? So the problem here is when substances are mixed, the chemical properties of each material determine whether a reaction will occur. Okay, because reactions are determined not by physical properties, but by chemical properties. Signs of a reaction are because of physical properties. Okay? After a reaction, I produce new materials with new physical properties. So as a result, I might get temperature changes, precipitates being formed, gases being evolved, okay? All of that, color changes, odor changes, all of that kind of stuff. Those are all because of the new substances having different physical properties. The reaction happens because of the chemical properties of the reactants. So what evidence do we have that a reaction takes place when substances are mixed? So we need to restate that in our own words in the form of a question to basically address what goes on in a chemical reaction. Okay? And maybe what are the signs? Right? Something like that. Okay, you need to, that's what we're investigating here. What happens in a chemical reaction? How do we know when it happens? That kind of stuff. Okay, so your problem needs to address that. All right. For our design and variables, so remember, we want to not only identify our manipulated, responding, and controlled variables, but we need to explain each. The explanation needs to include how is it being, if it's the manipulated variable, how is it being manipulated and why? Okay? For the responding variable, how is it responding? Why? Or how is it being measured? Okay? Something like that. And for each controlled variable, the explanation needs to be how is it being controlled? What effect would it have if you didn't control it? Okay, so for each controlled variable. Three controlled variables, yeah. Okay, same thing for your properties of compounds lab. Okay? 3 controlled variables. All right, so if we're looking at our variables here, here's how the experiment works. You are going to be combining different combinations of reactants. Okay, that's basically the procedure. The procedure is, hey, take these two things, mix them together and observe. Take these two things, mix them together and observe. So each time we mix two things together and observe, we're mixing different, okay, but let's not use things. What do we call the stuff that starts a reaction? See, there's a good chemical term for you. Okay, so maybe we're manipulating the reactants a little bit. Just putting that out there. Possibility / reality. Okay. Each time we mix different reactants, what are we hoping to see? Okay, we're hoping to see different products. What's that going to look like?
Oh, chemical.
Okay, we can't see chemical properties. What do I see? Okay, I'm looking for the signs of a chemical reaction. Each time I mix things together, I should see something that indicates a chemical change has occurred. Okay, that's what's responding to the fact that I've mixed things together. Okay, I mix these things together and I'm looking for this. Okay, our responding variable is always, what am I looking for? What's going to change because of what I did? Okay, but again, don't use the word I or we or us. Okay, I'm saying that, but you can't. So in your explanation, you need to tell me how is that happening? Why is that happening? One or the other, okay? But you need to kind of explain that in your explanation. Now you need 3 controlled variables. Your controlled variables are probably all going to be environmental. Okay? Because reactions can be affected by environmental conditions. Okay? So you can think up a few things, okay, there. But I would also say that one controlled variable should probably have to do with how you are combining the materials. Okay? If we're doing this fairly, we should probably always use the same amount. Okay? To observe and compare reactions, we should probably use the same amount of reactants. Right? And we'll do our best to be. All right, for our hypothesis, what three words go in? If, and, then. Okay. The if part needs to tell me what happens in a chemical reaction. Okay, that's what the if part needs to address. Okay, and I would say it would be a good idea to refer to Dalton's atomic theory about this, because he kind of stated it pretty well, especially in, I don't know, point number 4. Okay, that might be a good place to look for inspiration for your if part of your hypothesis. Right? The and part describes the experiment. Right? In this experiment, various reactants will be combined and the reactions will be observed, looking for changes in time. Okay? Okay. In the then part, you need to tell me how you will know if a chemical reaction has occurred. I didn't spell occurred right. It doesn't have 3 C's. Okay, so maybe you would mention something about the signs of a chemical reaction in the then part. By the way, RXN is shorthand for reaction. Okay, now the procedure, pretty straightforward. We're filling in all of these we're going to be performing these reactions. So we'll be mixing A and B. So in the first reaction, we'll be mixing sodium hydroxide, very strong base, and I mixed it really strong, with ammonium chloride. I also mixed that really strong. So you shouldn't miss the signs of the chemical reaction. However, remember that the reactions are not, or sorry, the signs of a reaction are not all visible signs. There may be other changes that you need to be watching for during a chemical reaction. Hint, hint, in this reaction, there's no visible sign of a chemical change. Okay? All right. For pair number 2, we're mixing C and D. So we're taking acetic acid, which is more commonly known as vinegar, except this isn't vinegar. Okay? Vinegar is 5% acetic acid, 95% water. This is 65% acetic acid.
So we don't want to drink it?
No, it's going to smell really vinegary. Okay, yeah. Okay, and you're going to mix that with sodium hydrogen carbonate, also known as baking soda. You've probably seen this reaction happen before, okay? Somewhere along the way. Okay, so you'll see that one. That one has some visible signs of a chemical reaction. Okay, pair number 3, you're mixing A and E, so that'll be sodium hydroxide, okay, and magnesium chloride. So we'll be mixing those two. Okay, and then we'll be looking at A and F, so you'll be taking sodium hydroxide and phenolphthalein. Okay, now phenolphthalein will be in a little squirt bottle. No, I shouldn't say drop bottle. Okay. Phenolphthalein, if you ever watch any like crime scene investigation shows, it's the stuff they use to test for the presence of blood. Okay, they put it on the end of like a cotton swab, and if there's blood, it turns pink. Okay, phenolphthalein is an indicator. It turns pink in basic conditions. It turns clear in acidic conditions because the pH of blood is slightly basic. Okay, it turns pink. Well, it's not a 100% reliable indicator, but it works pretty well, and it looks cool on TV. Okay. So we'll be doing that now. Pair 4 and pair 5 have to be done in order. All right. You can do the other pairs. You don't have to do pair 1, pair 2, pair 3. Okay. You can do pair 7, pair 2, pair 3, pair 1. But pair 4 and pair 5 have to go in order because you're using for pair 5 the product of pair 4. Okay? So in pair 4, you're going to be mixing sodium hydroxide and phenolphthalein. Okay? Then you're going to add acetic acid to that mixture. Okay? So that's the only one that has to be done in order. Okay. In pair 6, you're going to be mixing potassium iodide with lead 2 nitrate. Okay, observing that one. Okay, and then in pair 7, you're going to be putting hydrochloric acid on a chunk of zinc. Okay. All right, so those are your 7 reactions. Okay, what we're going to have to do is we're going to predict them first. Okay, and then we're going to go into the lab and see what happens. See if all of our predictions are correct or not. And kind of go with that. All right. So let's look at the predictions right now. Okay. So the way this will be set up is I'll have on the front bench, okay, all of the knowns. Okay. This time they're actually known, and I have their formulas in permanent marker on the sides of either the Erlenmeyer flasks. Okay. That's what these are. Or if it's a solid. Actually, I think I only have the sodium hydrogen carbonate in a beaker. I put the zinc is actually also in a Erlenmeyer flask, because you can just put a chunk of it on your hand. Okay, it is the only thing you should touch. Okay, in this lab, the zinc won't hurt you. It's in vitamins. Don't do it because it's a jagged piece of metal. You don't want to do that. All right. So the rest of them, and there'll be eyedroppers in each one. I am going to actually write on the bulb of the eyedropper which thing it comes from. It is really vital that you do not put the eyedroppers back in the wrong containers. Because if you do, well, it's not going to blow up, but it'll contaminate the solution and I'll have to make it again, and that's expensive. Okay, and we're almost entirely out of one of the things I made, like magnesium chloride or something like that. We're almost out of it, so I don't know if I have enough to make another container of it. Okay, so please be careful with that. Look at the bulb. Okay, if the stuff has come off, throw it away. Okay, if you can't remember where you got it and the label came off the bulb, it's probably on your finger. Okay, but if it comes off the bulb, just throw the eyedropper away. They're cheap, they're disposable. It's way better to throw one of those away than it is to contaminate the solution. Right? Okay, so that's what happened. These little bottles here, that's the phenolphthalein. Okay, so it's just in a little dropper bottle, so you pop up this little nozzle, okay, and you just put some drops in, okay, like 4 drops, all you need, okay, for this to work. Okay, you're going to be doing this in a watch glass, not the depression plates. Okay, yeah, I know. In the properties of compound lab, everything's really small, but we were trying to save materials. Okay, so now you're going to have a bigger container in which to do the experiment. Okay, so you'll be mixing those 2 things in there. Now, you want to do the mixing at your table. So put one of them in the watch glass and bring the other one over with it. Okay, so you might need to, fill up an eyedropper, turn it upside down, and walk over to your table, set the watch glass down, and do the mixing at your table. Okay, should you be taking the temperature of every one of them?
Yes.
Yes, it says that in the instructions, but okay, make sure you do that. So this thing here, it's about this big. Okay, it's like a giant contact lens. It's not that big. All right, everything gets put in the waste bucket afterwards. All right, so you take the watch glass over to the waste bucket with your wash bottle, spray it off, make sure everything gets in the waste bucket. The waste bucket, when you do this, it's going to be constantly fizzing and bubbling. It's going to look like a witch's cauldron. Okay? Okay, so the rest of the pre-lab goes like this. Okay, you've got to predict the products of these reactions. I'll help you with a couple of them because some of them are a little bit weird. Okay, this one here should be pretty straightforward because it's what kind of reaction? It's double replacement. Now, just so you know, NH4 ammonium is the only positively charged polyatomic ion that you have on your chart. It behaves as a metal. Okay, so when you're doing your switching, okay, that's the metal. Now, for this one here, this one's weird. It's because it's partially organic and partially ionic, it's written backwards. This is acetic acid, CH3COOH. Acetate is this ion here, and it's a -1 charge, right? That's actually in your table of polyatomic ions as well, right? And then you have H+, so it should actually, technically, be written like this, okay? HCH3COO, but it's never written that way. It's a funny thing with naming acids, okay? So that's what it should look like. So hydrogen is behaving as the metal, okay? And then you've got sodium, which is the metal, hydrogen carbonate, which is the non-metal, right? So it's, again, what kind of reaction? Double replacement, so you know how to swap and drop it. Okay, this one here, also pretty straightforward, double replacement reaction. You don't have to predict 4 or 5, because it's an indicator reaction, and we don't go over that, okay, in Science 10, so you don't have to predict those two.
So the prediction, you were not predicting like the reaction's going to look like, just like the
Just the products, yeah, you're just predicting the products, not what signs you're going to see.
Okay.
How do you get to those small numbers on the keyboard?
You have to go into the fonts. So, into and text, and then it's subscript. Yeah, so guys, if you want to put in the little numbers, you go, it's format, text, subscript. Okay? There should be a shortcut key, but I don't remember what it is. Control plus. Control plus? Yeah, something like that. Anyway, that's how you do it. Okay, I'll show you that tomorrow. We just got to get through this part. Okay, and then you got another one here. Okay, so pair 6, potassium iodide. Right, so you got some double replacement and a single replacement reaction. Have those predicted. We will not be doing a quiz tomorrow. I'm going to move it to Friday, so we have the whole class to do the lab. Okay?
Do you want us to finish the last one tomorrow?
You don't have to.